Okay.
Sir. So I'm actually just going to stand by. Audiovisual is coming, so they should be here. Oh, they're ready for time.
Yeah. Okay. All right.
We're good.
Great. Yeah, sure. Great.
He's our mic. He is airing the AV set off.
All right, well, why don't I just go over the administrative stuff while people file in. So the first thing is there's no class next Tuesday, right? Because Tuesday is on Monday's schedule because of President's Day. Actually, I only just realized that. Unfortunately, it means that you know we're sort of off to a slow start in this course. You know, you combine that with the snow cancellation, but you know that's okay. We'll we'll start out. We'll catch up, and so although there's no class next Tuesday, I will have my regular office hours then anyway, if anyone wants to come, like 11 to 12. And next Thursday, unfortunately, I won't be able to be here, but I'll have my postdoc, Robin Kothari, giving a guest lecture. He's really excellent. He'll be telling you about context-free languages, I think. Okay, so it'll just be a normal lecture. Let's see. So apparently the order for the Sipser book in the student bookstore. Can anyone tell me, did they try to get it, the book there, and were they able to get it? No one actually tried to get the book? Or you all just download it online or something? Okay, all right, fine. Okay. All right, well, if anyone actually wants a physical copy of the book, then you know it should be arriving to the bookstore, so you can get it there. Okay, so any questions about any administrative stuff before we get started? Yeah. Yeah, I think, you know, so I just, you know, we wanted to make sure that everything would work out well, but now it's set so that they're going to be posted at least very quickly. Yeah, and they'll be accessible to you, you know, whether we end up using them more broadly, that I have no idea, but you know, okay. So it's the first year that I'm doing this, but you know. You know, I'm surging forward into the new technological world. So, okay. So, any other questions? All right. So today we've got a lot to cover today. We're going to talk about the theory of finite automata and regular languages. So we already sort of defined finite automata a week ago, and we gave an example of a finite automaton. Okay, so remember, you know, a finite automaton is just like a computer that scans its input in one direction, say from left to right. Okay, so it reads a bunch of symbols, and as it reads them, it maintains some state. Okay, and it can transition to a new state, you know, depending on its current state and on the symbol that it's reading. Okay, and then at the end, it either you know, accepts or rejects the string. okay, depending on what state it ends up in when it reaches the last symbol. So that's basically what a finite automaton is. Okay, a very, very simple kind of computer. Okay, and to be a little bit more formal, and I just sort of invented my own variables last week, but I should probably try to stick to the variables that Sipser uses in his book. So, so finite automaton is specified by a set of states that it can be in. You know, and this is always a finite set of states, you know, hence the name. So we will call that Q. There's also a finite alphabet, so that's just the set of possible symbols that the automaton can read as it moves along. You know, a standard choice for an alphabet is just 0 and 1. You know, the binary alphabet, but you know, it doesn't have to be that. We could also consider larger alphabets. Okay, and then finite automaton also has a designated state called its start state. Okay, Sipser calls that Q sub 0. Okay, it's just, you know, the state that it's in before it's read any symbol, and then it has a designated a set of accepting states. Okay, so the automaton accepts if and only if, you know, it ends up in one of these accepting states in this set F. And then the thing that does the real work is the transition function, okay, which Sipser calls delta. Okay, and that's a function that just tells you, given your current state and given what symbol you're reading, what state do you go into next, you know, for reading the next symbol. Okay, so but that's all, you know, a little bit more formal than usually necessary. You know, usually we can reason about finite automata just by drawing pictures of them. Okay, and just, you know, drawing arrows to represent the transition function. Okay, so we did an example of a finite automaton last week. We did one that checks whether there are any ones in the string. All right, so let's do one more example just to, you know, refresh it in memory. Let's do a so do you all know what the Hamming weight of a string is? So if I have a so just a little bit of notation. Okay, first of all, if I write like 0, 1, star, that's just the set of all strings over the alphabet 0 and 1. Okay, so it's the set of all strings of any length. We'll see, you know, I think later in this lecture, formally what the star operation is, but it just means take as many of these things as you want to, okay, including none of them if you want. Okay, so 0, 1, star is the, let me write it, 0, 1, star is the set that contains the empty string, you know, that's fine, the 0 string, the 1 string, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, and, well, it goes on for quite a while. Okay, all fine. Okay, so a couple points to bear in mind here. So 0, 1, star is the set of all finite binary strings. Okay, so 0, 1, star is an infinite set. You know, it contains infinitely many strings, but every string that's in the set is finite. Okay, so star means, you know, repeat as many times as, you know, take as many of these things as you want, but, you know, at any rate, a finite number of them. Okay, we're not talking about infinitely long strings here. Okay, so this is the set of all finite strings, and of course, you know, the empty string, which means the string of length 0, you know, is also a finite string, so that also has to be included in the set. Okay. By the way, you know, things to bear in mind. This is probably stuff that you know, you would have seen in 604.2, but the empty string, you know, is not at all the same thing as the set containing the empty string, right? Or the, you know, or let's say, you know, if we viewed these as sets of strings, right? This is a set that has no strings in it, okay? But this is a set that does have a string in it, namely the empty string, okay? So, you know, it's like a Lewis Carroll type of thing. But yeah.
Same thing as
Yeah. yeah, okay. So I write it like this, but you know what? I think Sipser calls it epsilon. So let me call it. Thank you. Let me call it. Let me write it as epsilon because that's that is what Sipser calls it. Okay. Again, just these are just matters of notation, right? But yeah, this being clear about this kind of thing, something that can be useful and PSETs, midterms, stuff like that. Okay, so good. So okay, so now if we have a string in 0, 1 star, so a finite binary string, then if I write like this, the Hamming weight of the string is just the number of ones in it. Okay, that's what Hamming weight means. And now, one thing we might be interested in is the set of all strings with a finite. Sorry, the set of all strings, let's say, with even Hamming weight. Okay, so let's talk about a finite automaton for that. First, just a little bit more, terminology. This is just purely, the definitions. Okay, so okay, so first of all, if I have a set of finite strings, so like a subset of 0, 1 star, this I call a language. Okay, and the terminology is kind of archaic, right? Because most of these, the languages that we'll see in this course, and we'll see a lot of languages, and they'll be neither like, English nor Chinese, nor will they be like C or Pascal. They'll be like, the set of all strings of even Hamming weight or something like that. Okay, but the terminology in this field is just any set of strings whatsoever can be a language. Okay, the original reason that people were studying this kind of thing, had to do with human languages or programming languages, but it became more generalized. Okay, kind of like in the history of math, right? Originally a function meant something like x squared or sine of x or something reasonable, right? And only later did a function come to mean any possible mapping from this input set to that output set. Okay, so language is any set of strings, over some alphabet. Here, the alphabet is 0, 1, and we'll say that a machine, like let's say a finite automaton, recognizes or accepts the language. In this, for now at least, they mean exactly the same thing. Okay, M recognizes the language, M accepts the language if M accepts all the strings over that alphabet that are in L, and it rejects all the strings over that alphabet that are not in L. Okay? So it accepts exactly the strings that are in the language. Okay? That's what it means for it to sort of recognize the language. Okay? So now if we have a finite automaton, M, that we can write L of M for whatever language is recognized by M. Okay, and here we're using we're using the observation, if you like, that every finite automaton recognizes exactly one language, right? Namely, just look at what it does, and take whatever set of strings that machine accepts. which might be the empty set, which might be the set of all strings, which might be something in between. Whatever set of strings M accepts, that's L of M. Okay, that's the language that it accepts. Okay, and then our last definition is that we call a language regular if there is some, so L is regular if there's some M, such that L equals L of M. Okay? In other words, a language is regular if it is recognized by some finite automaton. Okay? So the regular languages are just, those languages that, you can design a finite automaton to recognize them. Okay? So, all right, so with that, out of the way, I could now claim something like, let me consider the language that consists of, let me make it odd Hamming weight just to mix things up a little. The set of all x's, and here it's implied in 0, 1 star. So let's define L to be the set of all finite binary strings that have odd Hamming weight. Okay? And now I claim that this language is regular. Okay? Now to show that it's regular, it would suffice to just come up with a finite automaton that recognizes this language. Okay, so can anyone suggest to me how would we design a finite automaton that recognizes this language? Yep.
2 states.
Mm-hmm. Yep.
Just pick arbitrarily one as the start state.
Yeah. All right. This one, I'm way ahead of you. I already picked it. Yep.
You go make zeros to move back to the state that it's in.
Yep.
And 1,
Excellent.
and then you make the 1 that's not the start state that makes it.
Yeah. All right. Excellent. That's exactly right. So there we have it. A 2-state finite automaton for checking whether our string has an even or an odd number of ones. Right? And you see how it works. Every time there's a 0, you stay in the same state. Every time there's a 1, you go to the opposite state. Okay? And and by the way, these 2 circles, that's the notation we use for an accepting state. Okay? Like we circle the circle if that state is accepting. Okay, now you'll remember that last week we also did an automaton that checks whether the string has any ones. And that one looked like this. Right, just a little change to this one. Okay. And so that one recognizes a different language. Okay. Okay, so now here's a question. Let's let L be the language recognized by this automaton, right? Let's let L prime be the language recognized by this one, okay? And now we could play games. Like I could say, well, what if I'm really interested in the intersection of L and L prime? Okay, so now I want to combine the two. What does that mean? Well, what it means is this is actually just, I haven't done anything here. Okay, because in this case, one language is a subset of the other one. I'm just here. I'll tell you what. Let's make it a little more interesting. Yeah, how about, or I could do, here, I'll make this one check for zeros. There we go. There we go, problem solved. All right. All right, good. So we've got L prime is the language of all strings that have a 0 in them. L is the language of all the strings that have odd Hamming weight, right? These are two incomparable languages, right? There are, there are strings like 111 that have odd Hamming weight, but that have no zeros in them, right? There are strings like 000 that have that have no ones and that do have zeros and that have even Hamming weight. And then there are strings like 001 that do have zeros and that have odd Hamming weight. Right? Okay, good. So now let's consider, L intersect L prime, which is the language of, all the strings that have at least one 0 and odd Hamming weight. Okay, how could we design a finite automaton for this language? Can anyone come up with one? So there's a slightly more interesting example. Maybe. Yeah. Yeah. All right. So excellent. So in fact, what's your name? Hung-Yi? Okay. Yeah. So what he was suggesting is actually something that solves a much more general problem than the specific one that we were talking about. Okay. So in fact, let's just go ahead and and just abstract away from this particular L and L prime and just say something more general. Okay. If you have any two languages that are regular, then their intersection is regular also. This I claim. Okay, so how can we see that? Well, a simple way to see it is via what we'll call the product construction. Okay, where all you do is so let's take our first automaton, right? It looked like this. One, and here was our start state, here was our end state, right? And let's just make two copies of it, put them side by side. Okay, I'm letting accepting be the up direction here. Okay, fine. Okay, and now let's take the second automaton and let's put that one in the left to right direction. Okay, so we've got what 1, 0, 0, 1, 1. 0, 0, 1. Okay, and now I'm interested in the intersection, which means okay, so my start state should be what? Anyone? The start state of my new automaton? Like let's say okay, I can make the choice arbitrarily, I guess, but let's say the bottom left one will be my start state. Okay, and let's say my accept state will be what? Anyone? The top right. Yeah. So what am I doing here? I've just basically defined a finite automaton that just simulates having both of these finite automata at once. That's all it does, right? So it's like the state of each of these individually was one bit of information, right? So with this four-state automaton, it's keeping track of 2 bits of information, namely the state of each one individually, right? One of them in the left-right and the other one in the top-down. Okay, and then I'm saying I want to start in the state that corresponds to the start states of both of the automata. And I want to accept if and only if we end up in the accept states of both of the automata. or if we end up in states that are accept states for both of the automata. Okay, so so this is this is the sort of thing that we call a closure property, right? We'll see more examples of that, right? Where we have some family of languages, and then we verify that you can do something to the languages, and you still stay in the family. Okay. Good. So here's All right. Here's a next question. Sorry. Yeah.
Was it a finite set of automata? There's two like zeros from the first start state, like every state is.
Oh, I'm sorry. Oh, right. Okay. So let's go. Yeah, you're absolutely right. Okay, so the arrows, yeah, so the arrows that I drew were stupid. All right, so but the idea is sound. So let's take it from the top. All right, so if you're in, by the way, this is Robin. He'll be guest lecturing next week. Okay, so if you're in Q0 and you see a 0, then you want to stay where you are in terms of the first automaton, but you want to transition in terms of the second automaton, right? So we could say we want you to go like this. Okay, if you see a 1, yeah, you're right. So the arrows, you have to be careful in writing them. Okay, I was sloppy. So if you see a 1, then you want to move in the first automaton and also and stay where you are in the second one, which means that, right? Okay, good. Up here, what do we do? So if we see a 0, we want to stay where we are over here, and we want to move over here. And if we see a 1, we want to move down over here and stay where we are over there. So 1. All right, well, you can continue filling it in like this. Okay, but you see what I'm doing? I'm just taking like the product of, this one turned on its side. So let's draw this one in the appropriate way. Wait. Okay. Good. So the point is that the one arrow here determines whether we move up or down or whether we stay where we are. If we see a 1, the arrow over here determines if we see a 1, do we move left or right, or do we stay in the same left-right position that we were in before, and then we combine those two pieces of information to get our arrow, for that symbol and for that state. Okay, so that's how it works. Yeah, it's early in the morning. Okay, so any questions about that? Okay, all right. So let's do another question. So if I draw a bar over L, that means the complement of L. Okay, and that means the set. The set of all strings in my underlying, set, like 0, 1 star, that are not in L. Okay, that's all the complement means. All the strings that are not in L. Okay, so complement is another, very basic thing that you may want to do to a language. Okay, and so now we can ask the question: if L is regular, then is L complement also regular? Can anyone? Yeah.
Yep,
Exactly. Yeah. This is quite an easy one because all we have to do is just switch the accepting and rejecting states, right? And then we're done. Right? Like for example, here's an automaton that recognizes all the strings of odd Hamming weight. If I instead wanted an automaton that recognized all the strings of even Hamming weight, oh well, great. Now this is Now this is an accepting state, and now this isn't. Right? So this is easy. Okay. We'll see examples later where some of these closure properties sometimes are not true, or where they're true but they're much less obvious. But yes.
Does that work with strings?
It works with empty strings same way it works with everything else. So like if the empty string is in L, then the empty string is not in L complement, and vice versa. Yeah. Okay. Good. So all right. So we've seen that the regular languages are closed under intersection, and they are also closed under complement. Okay. So now. Here's the next question we could ask. Are the regular languages closed under union? Well, yeah. That's a very interesting thought, and but there's a reason why the fear is unfounded. The reason is that yes, we could build up any language as a union of a bunch of other languages, but in general, that could be an infinite union, right? And that could lead to an infinite number of states, and then and then we no longer have a finite automaton. Okay, so yeah. Mm-hmm. Yeah. Yeah, you can absolutely do that. So that would be one way to answer this. In fact, another way is that the answer just follows from what we've already seen. Okay, you can just, because think about it. What is L union L prime? Well, by De Morgan's law, you remember De Morgan's law from last week, it's just the complement of L intersected with the complement of L prime. All right, so there we go. The magic of De Morgan, right? And we just got a result for free. Okay, see that? So okay, so let's we've seen examples of regular languages, how to build new regular languages out of old ones. Actually, just following up on the question that we just had. Here's a quick sanity check. Okay, so let's say that a language is finite if it contains finitely many strings, right? Only finitely many strings. Okay, so then is it true that at least all of the finite languages are regular? Yeah, how come? Mm-hmm. Yeah, that's basically exactly right. If you're if your language is finite, then all you have to do is just make a big old binary tree, right? Where you just create lots and lots of states as needed, like this. You start here. This is your initial state. You read a 0 or you read a 1. That tells you which leaf to go to. And since we're only interested in accepting finitely many strings, we can we can terminate this tree at a finite number of different possible accept states, and that's really all we have to worry about, right? And if say you're here and if you read something where now you've read in a string that's not the prefix of any string that's in the language, then all we have to do is we can just send the automaton to some purgatory where it has to suffer forever or something, okay? And never accept, right? Like this is not an accept state, but there's no possible way to get out of it. Okay, if you don't like that, if that sounds too, cruel or something, you can always just, you can always just draw it like this, right? Or just say, I just send this automaton off into space. I just, or you can just say like I send it out to reject, right? Because we know that you could fill that in if you wanted to. Okay, so all right, so all finite languages are regular, which means like the set of all possible games of chess that lead to a win for white and that could be played within a human lifetime. So right, that may sound like a complicated set. That's perfectly regular. Okay, so so in some sense, like the sorts of questions that we'll be talking about in this course sort of only get activated in some sense, when we're talking about infinite sets of languages. Well, that's not quite true with circuits, which we talked about last week, right? Circuits had the interesting property that we can take a completely finite problem, like deciding which player has the win from a given chess position. And we can ask the question, what is the size of the smallest circuit that solves that problem? Right, so circuits are interesting even just for completely finite problems. Okay, but once we've moved from a non-uniform to a uniform model of computation, like finite automata, right, when where the inputs can have any size, then sort of things only become interesting once we're talking about infinite languages. Okay, so an obvious gap in what I've done so far is I haven't given you a single example of a language that's not regular. All right, so once again, it's like you see a definition, you see no examples of anything that doesn't fit the definition, right? It's you're just kind of wasting time, right? So all right, so so let's try an example. So let's say I am interested in the language of palindromes. I'll call that P. Okay, palindrome is just a string that's the same, read backwards and forwards. Famous example is, a man, a plan, a canal, Panama. Okay, or ABBA, like the music group. Okay, or zero. Let's just talk about palindromes over the 0-1 alphabet. So then 0-1-1-0 is a palindrome. 0-1-0-1 is not a palindrome. Is the empty string a palindrome? Yeah, sure. Same backwards and forwards. Likewise, 0 is a palindrome. 1's a palindrome. 0-0 is a palindrome. Is 0-1 a palindrome? Nope. Okay, so so this seems like a very, very useful capability for your computer to have to tell you whether a string is a palindrome or not. Okay, so let's design a finite automaton that will recognize the set of palindromes, the language of palindromes. Okay, well, how can we get started doing that? Well, Basically, you've got a string of some, unknown length. You start at the beginning. Okay, and we need to scan it through from left to right. And then at the end, we need to know whether the, basically just, let's, for simplicity, restrict our attention to strings of even length. Okay, let's just start with a simpler problem of recognizing palindromes of even length. Okay, then, in that case, our problem is just to see, is the second half of the string the reverse of the first half, right? Which, in this case, clearly it is. Okay, so it sounds pretty simple to solve this problem. Okay, all we've got to do is design an automaton that just snarfs up the first half of the string, stores it in memory, and then compares it against the second half of the string. What's the problem with that, anyone? Yeah. Yeah, exactly. I mean, first of all, we have no idea in advance, how long the string is going to be, right? And look, maybe I'll even be generous to you. I'll put a special symbol in the middle that will tell you when you've reached the middle of the string, okay? Even then, I claim that there would still be a difficulty. Yeah. Yeah, well, in some sense, it's, intuitively, there's kind of a problem here, right? Which is the whole point of a finite automaton is that it has a finite amount of memory, right? It has some fixed number of bits of memory, which is namely the base 2 log of the number of states of the automaton, right? That you could think of as measuring how much memory it has, okay? But the amount of memory that it has is not allowed to grow with the length of the string that it's processing. Okay, and so somehow we want some automaton with some fixed number of states to recognize palindromes of arbitrary length. Okay, but it seems like there's an inherent problem here, which is that the longer the string is, the more the automaton is going to need to remember, right? Because you're going to have to sort of remember the whole first half of the string, if you want to compare it against the second half, right? You only get one. Remember, you only get one pass through this thing, right? But it seems like there's sort of an inherent memory bottleneck here. Okay. But now that's an intuitive argument. That's basically an argument that I can't think of a way to do it, right? And in this course, we're not going to be quite satisfied with that kind of argument. Okay, we're not going to sort of insist on hair-splitting rigor for its own sake, but we'll try to make sure that we have enough rigor that we don't that we typically don't get wrong answers. Okay, so let's see how to make this argument a little bit more rigorous. How can we actually prove that this language of palindromes is not a regular language? Okay, so the proof of this is actually going to use one of the deepest facts in all of math and science, and that's called the pigeonhole principle. Okay. The pigeonhole principle says that if you have n plus 1 pigeons and you're trying to put them into n holes, then some hole is going to have more than one pigeon. Okay, incredibly useful fact. We'll use it again in this course, right? But in this case, certainly as a special case of the pigeonhole principle, if we had a finite number of holes and we had infinity pigeons, then surely some hole will have to accommodate more than one pigeon. Okay, you agree with that? Yeah, I don't need to prove that. Okay, so all right. Well, so taking the pigeonhole principle as given, let us give a proof by contradiction. So let us suppose that there were a finite automaton that recognized the language of palindromes, and let us then derive a contradiction. Okay, so what we can do is we can consider the set of let's just start listing all the palindromes. All right, I mean, there's the empty string, of course. Then there's 0, 0. There's 1, 1, right? There's, say, 0, 0, 0, 0. There's a palindrome. There's 0, 1, 1, 0. There's 1, 0, 0, 1. There's 1, 1, 1, 1. There's 0, 0, 0, 0, 0, 0, and so on. You know, and I'll just split this down the middle. Okay, so we could imagine having an enormous list of all the possible palindromes of every possible length. You know, an infinitely long list. Okay, now what we're going to do is we're going to say, let's let M be our finite automaton that we, you know, imagine is able to recognize this language, you know, is able to accept these strings and only these strings. Okay, M has some being a finite automaton, it has some finite number of states, right? Call that number K. Okay, say it's K states. Okay, well, however big K is, I claim that, you know, so now what I want to do is I want to just look at what state is the automaton in when it crosses the midpoint of each of these strings. This is what I want to do. Okay, so just, you know, after it's read this symbol, what state is it in? You know, let's call that that state here. We'll call it, you know, S1, S2, S3, whatever it is. You know, and each SI can be labeled by some integer from 1 to k, telling you which state it's in. Okay, now, can all of these SIs be distinct? No? Why not? Yeah, the pigeonhole principle, right? There's only a finite, you know, there's only k different states, but there are infinitely many palindromes. Okay, which means that at some point, you know, the same state has to occur twice in this list, right? Okay, so in other words, you know, there must be some pair. What we're saying is there must be some pair of palindromes. Call them. So by the way, by xt, I'll just mean like the reverse of x, right? Maybe I should call it r for reverse. I was calling it T for transpose, but that's more obscure. Okay, so let's call it XXR. Okay, so any even palindrome has the form XXR, right? So what we're saying is that there have to be two strings, two palindromes, XXR and YYR, such that our finite automaton M is in the same state after scanning X as it is after scanning Y, right? You know, this follows from the pigeonhole principle, right? Because there's just infinitely many choices for the left half of the string, but there's only finitely many states that we could end up in after scanning that left half. Okay, so say we end up in the same state S here as we do here. Okay, now can anyone sort of finish this off? Can anyone, you know, deliver the finishing blow? Yeah.
If you're in the same state,
Mm-hmm.
string,
Yeah.
then you have no way of knowing which string you're actually in when
Mm-hmm.
you're in that state.
Mm-hmm.
Because it's possible to like provide a false positive, like say X, Y, or.
Mm-hmm. Exactly. That's precisely right. Okay, what we can do now is just splice the two strings together. We can make XYR, right? Or we can make YXR. Okay, these strings, you know, by the assumption that X and Y are different, these strings are not palindromes, right? You know, and yet I claim that M must accept them. okay? Because when it reads x, y, r, well, it reads x, and then it's in the state s, and then it reads y, r. But we already know that if you're in the state s and you read y, r, then you're going to accept. So you're going to do it here also. Yeah.
Possible to pick sets x and y, which end up in the same state in the middle, such that x, y, r is a palindrome?
Well, so I claim that x, y, r is never going to be a palindrome. Does anyone see why? Yeah.
Because then they would both originally have to be the same palindrome.
Yeah. I mean, in some sense, right? They're let's see. Oh, so okay. So maybe all right. It's easier if I it's all simpler if I oh, you know what? You actually you do raise a good point, which is okay. So this is all all right. You know what? Yeah. Okay. You know what? You're right. Okay. Again, I'm terrible with details. Okay. But this is let's say that there's like I said before, that there's a stop symbol. There's a special symbol in between x and y that tells you when you've reached the middle. Okay. In that case, the argument that I gave would just work verbatim, right? If there's a delimiter, right, that tells you, when have you reached the end of x, and when have you reached the middle of the string, right? Okay, you agree that in this case the argument works. Okay, now if you're absolutely right, if we don't have a delimiter, then there is a technical problem, which is that you could have, for example, that x would be 0, 0, and y would be 0, 0, 0, 0. Right? So there are two strings of different lengths. Okay? And then these are different strings, and yet you concatenate them. You concatenate x with yr, and you get a palindrome, namely a string of 6 zeros. Okay. Can anyone think of a way to solve that problem? Okay. I can think of one way that's really, really simple. Namely, we could simply say, look, by appealing to the pigeonhole principle, however large k is, not only are there going to be two x's and y's that lead to the same s, there are going to be two x's and y's that lead to the same state s, and that moreover have the same length. Okay, because the length we can just make as long as we want, right? And we can, in particular, make the length L something such that 2 to the L is much larger than K, right? And then once we do that, then we're done. Okay, good. So this is how just by staring at the language and just by giving an argument, we can give a perfectly rigorous proof. At least if we think about it and we patch the problems, we can give a perfectly rigorous proof that language is not regular. So, we can show in particular that, there exist non-regular languages. Not everything that's out there is regular. Now, in tomorrow's recitation, you'll and also in the Sipser book, you'll see something which is called the pumping lemma, which is a humorous name. But all it is sort of a way of formalizing the intuition that I just showed you. Okay, so it's a way of formalizing this intuition, about the pigeonhole principle into just sort of a machine that you can just sort of turn the crank without even thinking about it, and you just verify that if your language has, satisfies such and such properties, then you can make a pigeonhole principle type of argument that will show that your language is not regular. Okay, so But when you look inside, this is sort of all that's going on. On the P set, there's a problem, I think, to prove another example language is not regular. Okay, and in general, if we ask you to prove something is not regular, you can do it whichever way you want. You can use the pumping lemma that you'll see in recitation and in Sipser's book, or you could just argue directly using the pigeonhole principle. Okay. All right. So we've seen then that finite automata are actually kind of weak, right? Which maybe is not such a surprise. I mean, they look weak, right? But yes, you can use it to check if there's any ones in your string, or if your string has some, in fact, has any designated substring in it. Yes, you can even check whether your string has an even or an odd number of ones in it. But even just checking whether your string is a palindrome, which seems like a pretty simple program to write, but that's already beyond the capabilities of finite automata. Okay, and essentially because finite automata can't count, right? This is sort of the slogan to remember, right? They've got only a finite memory. Finite memory can't count to arbitrarily large values. Okay, so let's try to come up with a more powerful model. Okay, and there are different ways that you could do that, but there's one that was invented by Michael Rabin in 1959 or so, and it was especially influential for the development of computer science. And this is called non-deterministic finite automata. Okay, so this was a very bizarre concept when first invented. Okay, because this is a finite automaton that's going to be based on the principle that when you see a fork in the road, you can take it. Okay, that a finite automaton that's somehow allowed to explore multiple paths at the same time. Okay, or sort of do multiple different things somehow at once. It doesn't have to be deterministic. Okay, so let's be a little bit more formal. So one way to think of an NDFA is that it's like that product automaton that I incorrectly drew earlier, and Robin caught me. Like that was an example of one. Okay, so an NDFA is basically a finite automaton, but where you're allowed to have multiple arrows emanating from the same state with the same alphabet symbol. Okay, so you're allowed to say, like if you're at this state and you see a 0, then you can either take this path or you can take this one. Okay, you can either transition to this state or you can transition to that one. Either one is fine. In fact, you're even allowed to have no arrow emanating from a state with a given alphabet symbol. Okay, so you're allowed to say if you're at this state and you see a 0, sorry, you're just up a creek. Okay, there's just nothing for you to do at this point. Just terminate. Okay, you can do that also. Okay, you can have any number of paths with the same alphabet symbol, including 0, and then. So then how do we interpret this? Well, the rule is we say that the automaton accepts if and only if there is any possible path, consistent with the input that you've seen that leads you to an accept state. Okay? So to be a little bit more formal, So an NDFA is defined almost the same way as an ordinary finite automaton, which, with retroactively, an ordinary finite automaton, we'll call, can anyone guess what? Deterministic finite automaton, or DFA, okay? DFA is the ordinary kind. It's also Doctor of Fine Arts, okay? But NDFA, I guess non-Doctor of Fine Arts, is the kind where you're allowed to have multiple transitions. So once again, we've got a finite set of states, finite alphabet, and then we've got a transition function that takes as input okay, there's one point here that I want to discuss. So we have a transition function that takes as input basically, the current state and an alphabet symbol, and it maps you to a subset of possible states, right? So it says, if you're in this state and you're reading this alphabet symbol, then here is the set of states that you're allowed to transition to. Okay? So that's what the transition function does. Now, there's one additional detail, which is really just a matter of convenience. Okay? And the detail is that we're also going to allow what we call null transitions. Okay? And a null transition just means an arrow that you're allowed to take even without reading any symbol. Okay? So if we have an arrow labeled by epsilon, right, then you're allowed to just follow that arrow, if you want to, without even, before you've even read the next symbol. It's like you're playing a board game and like you get to jump for free. You get an extra turn or something. Okay. Now null transitions. We can it will follow from things that we prove that they're never actually necessary. Right. You can always get rid of them if you don't like them. But they'll sometimes make finite automata more convenient to write down. Okay. So we'll include them. So this is just saying that you're also allowed to specify a set of states that you're allowed to move to, even without reading any symbol. Okay, and then just like before, we've got a designated start state, Q0, and we've got a set of accept states, F. Okay, and then the automaton accepts, if and only if there is some path consistent with the input that leads you to one of the states in F. All right. So what's the point of all this? This seems like a lot of metaphysical baggage for for what end exactly? Well, claim that non-determinism can sometimes make it much simpler to construct a finite automaton that does something that you want. So let's give an example of that. Let's see. Okay, let's consider the language consisting of all x's such that the third to last bit is a 1. Okay, so that's, so now you say, is this a regular language? Is this not regular? Well, okay, I claim with enough effort, you could design a DFA for this language. I could leave that as an exercise for those of you who are interested, although it will sort of be trivialized by the end of this lecture. Okay, but you can do it. You can design a DFA for it. It's not quite obvious how to do it because, after all, how do you know when you've reached the third to last character? Right? You're just reading things one by one. You don't even know, whether the character you're now reading is the third to last. Okay, so you could imagine that, you deal with this, you maintain a buffer of characters, and so that at any point, if it so happens that you've reached the end of the string, then at that point, you still remember what was the third to last, right? You can imagine doing that by maintaining a buffer and then constantly just throwing bits out of the buffer, if they're not among the three that you saw the most recently. Right, so that way you'd only be maintaining a finite amount of state at each point in time. So you're still a finite automaton, but you'd always be remembering what was the third to last character that you saw. Okay, so that's a way you could do this, but it's a little bit complicated. Okay, now how could we design a non-deterministic finite automaton that does this more simply? Well, all right, so let me get you started. So we'll have an initial state, Q0, and I'll say, if your reading is, no matter what you're reading, you can always stay in this initial state as long as you like. That's fine. Okay? And then what's going to happen? Anyone? Huh? Well, okay, at some point when you see a 1, you're allowed to go over here. Okay, again, we've got 2 arrows, both labeled by 1, emanating from Q0, but that's fine, because we're in NDFA. Okay, then what do we want next? Anyone? Well, yeah. Mm-hmm. Yeah, and yep. So this is the accepting state, and there we go. Okay, so I claim that this should work for us, right? Because this is saying, so now the question is, under what conditions, will there exist a path that leads to the accepting state? Right. Well, what does a path have to look like? It can hang, it can just waste time, dawdle around here as long as it wants. But then at some point, there's got to be a 1 in the string, and then there's got to be 2 other things in the string. Right. So at any rate, the third to last character has got to be a 1. And any time the third to last character is a 1, then there will be a path like this that ends at the accepting state. All right. So good. So that's our NDFA. All right. So now, the type of question that, we'll sort of train ourselves to, immediately ask in this course when, we encounter a new notion is, well, is it equivalent to the notion that we saw before, or isn't it? Sorry. Okay, so I could loosely phrase that question as, does NDFA equal DFA? This is going to be like our first baby version of the P versus NP question. Okay, and the first thing people like to say is, well, so if N is 1, if D, F, or A are 0, okay. But let's try to answer this for real. So actually, I claim, and this is kind of surprising and kind of interesting if you've never seen it before, that everything that can be done by an NDFA can also be done by a DFA. Or to put it differently, the set of languages that can be recognized by an NDFA is precisely the set of regular languages, the set that we already defined. So we don't gain any new expressive power by allowing non-determinism. It might make our finite automata simpler to construct, but it won't let us recognize any languages that were literally not recognizable before. Okay, so how do you think we could prove this? The outline is pretty immediate, right? What we want to do is we want to start with any NDFA and then construct a DFA that simulates it, that does the same thing, right, or that recognizes the same language. Okay, so all right. I mean, I guess the first thing we have to say is yes, like with most of these things, there, at least there's one direction that's pretty obvious, right? If you had a DFA, then certainly you could construct an NDFA that does the same thing, right? Because, well, just take the DFA that you had, right? That will count. Okay. By the way, this is there's a principle that I'll sort of appeal to many times in this course. I call it the Superman principle. Okay. It says if you're Superman, you can always at least simulate Clark Kent. Okay. You can always just sort of ignore your superpower and just do the thing you would have done without it. Okay, so in this case, if you're an NDFA, certainly you can simulate a DFA. Okay, so the interesting direction is the opposite one. How can we take an arbitrary NDFA, say M, let's say that has k states, and now we want to simulate it by some DFA with some other finite number of states. Okay, so how, so it's not obvious, right? Because the, NDFA is able to, have all these transitions going on at once. It can be, in some sense, following all these different paths at once. But, but if we were trying to just maintain the state of our NDFA by just a deterministic finite machine, like what information is it that we would have to remember? Let's come at the question that way. Yeah. Exactly, yeah. So the key idea here is that we're going to take an entire set of possible states in the NDFA, and we're going to map that onto a single state in the DFA. Okay, so we'll have one state in the DFA that represents the set of all the states that we could have possibly reached at this point in time if we were in the NDFA. Okay, and so this is called the power set construction. Okay, and what it's going to do is it's going to take an NDFA with k states, and it's going to produce a DFA with 2 to the k states. Okay, so there's an enormous blow up here in the number of states. And in fact, one can prove, I'm not going to do it, but it's interesting to prove that this blow up is unavoidable. Okay, so there are NDFAs that can only be converted to DFAs, by exponentially increasing the number of states. Okay, but what's an exponential increase between friends, right? Where the result is still going to be a DFA with some constant finite number of states, and so we've proved the language is regular, so we're happy, right? So okay, so it's probably so like you can read in Sipser, he writes out a full formal proof of the power set construction and the fact that it works. It's probably easiest just to do it by way of example, because once you see an example, I think the idea is clear. So let's do this one here. And just to make things a little bit more manageable, let me say that what we were actually interested in was the set of all the strings where the second to last bit was a 1. All right, good. So I've just trimmed this a little bit. All right. Okay. Okay, now the idea with the power set construction is that we're going to have one state for every possible subset of states of this NDFA, right? And not all of them might turn out to be relevant, but let me just write them all down anyway. Okay, first of all, okay, so one thing, I guess it's not 2 to the k, it's actually 2 to the k minus 1. All right, because I don't actually care about the empty set. I'm never going to have an empty set of states. All right, so let's just start with, I could be in 0, by which I mean Q0, right? I could be in 1, I could be in 2. I could be in 0, 1, I could be in 0, 2, I could be in 1, 2, or I could be in 0, 1, 2, right? And each of these represents like, the set of states that you could have reached, at this point in time, right? If, given the section of the input that you've read so far. Okay, so now let's fill this in. So if you were in state Q0 in this NDFA and you read a 0, then where can you go? 0. Okay, if you read 1, then where can you go? Well, if you read 1, you can go to 0 or to 1. Right, you have two choices, which means that the 1 arrow, and there has to be only one arrow over here because this one's a DFA, that one is going to go over to 0, 1, right? Okay, if you're in state, you know what? Let's skip this. Some of these states are never going to be reachable anyway, so we don't even care about them. All right. Let's say that you're in state. Let's say that you could be in state 0 or in state 1. Okay, and now you read a 0. Now where could you be? Well, if you were in 0 and you read a 0, then you're going to stay in 0. If you were in 1 and you read a 0, then you're going to be where? 2, which means that now you could be in 0 or 2. Okay, if you were in 0 or 1 and you read a 1, then now where can you be? Now you can actually be anywhere, can't you? Yeah, you could be 0, 1, or 2. Okay, and so forth. So we fill in the thing like this. People understand that? Okay, and then what should our accepting states be? Yeah, our accepting state should be anything that contains a 2. Yeah, exactly. And what should our initial state be? Our initial state should just be 0, right? And sometimes I'll write that just by drawing an arrow that comes in from nowhere with an epsilon transition. Right. Okay. So yeah. So the initial state, where we start in state 0, and then this models everything that happens. Okay. So and notice already that this this lets us deduce things that are not entirely obvious. Like, for example, let's say that I just first showed you the definition of an NDFA, and I had asked you, take the set of languages that's accepted by NDFAs. Now, is that language closed under complement? Okay, well, it's not, not obvious, right? Given an NDFA, how do you construct an NDFA that accepts the complement? Of what the first one does, right? Well, it's not clear, but one way to do it is, well, at any rate, you could just convert that NDFA to a DFA and then take the complement of that. Okay, all right. So there's one more thing in this happy family, I guess, of computation models. With which I'll finish the lecture, and that's the regular expressions. Okay, so those of you who have done any programming, any compiler stuff, you've probably or even just used decent text editors. You've probably messed around with regular expressions in the past. They're very, very useful. They are basically they're ways of specifying sets of strings. Okay, so in other words, languages. Okay, and they are built up out of a few symbols, like you have some alphabet, of basic letters, like in this case, let's say there's 0 and 1. Okay, and then you're also allowed to do concatenation which means, if you have any two regular expressions, you can just put one next to the other, which, and I normally won't even write the concatenation symbol, because that just means just put two things next to each other, right? And you're also allowed to have an or symbol, which means, take either this or this, okay? And then you're allowed to have what's called the star symbol, which means take, any number of copies of this thing that I've starred, and, that you want, including 0 copies, okay? And then you're allowed to have parentheses, so you're allowed to nest expressions, recursively inside each other. Okay, and that's all you're allowed to do. Okay, so let's do some examples. Let's say that you had a picture of a sheep, in your computer, and it was called, it was either a JPEG or a GIF file. You can't remember which. Okay, and it was called ba dot whatever the extension is, but you can't remember how many A's there were in the ba. Okay, so what would be a regular expression for searching for this file? Yeah. BA star dot.
GIF or JPEG.
Yeah, dot open parenthesis, GIF or JPEG. Okay, right, and as I said, any decent file search utility will actually let you do stuff like that. Google also lets you use regular expressions, right? So you can do like more sophisticated searches that way. Okay, so good. So let's now just let's do another example. How about what would be a regular expression for the language of all the strings that have either a 000 or a 111 somewhere in them? Yeah, question? Oh, okay. So yeah, you're right. You can add all kinds of things that like would make things more convenient for ourselves, right? If I claim that if you wanted a symbol for one or more copies of this, then we can actually just simulate that using the star symbol only. How would we do that? Well, we could always just do something like this, right? So I say, look, take the one copy and then take as many additional copies as you want, including 0. All right, so I'll just stick to star, but though if you wanted to use plus, to mean like one or more, like when you do your PSAT or midterm, it's okay. Maybe just put a note to just, make it clear to the grader that it's what you're doing. Okay, so. All right. So let's just stick to these symbols for the lecture, I guess. So how could I write a regular expression that says there is at least one substring in my string that's 000 or 111? Let's say that my string is just a string of zeros and ones. Yeah.
0 or 1 star.
Mm-hmm. Yep, excellent. Good. So there's a nice example of a regular expression, which picks out the set of all strings that contain either this or this as a substring, right? And on this here I should. And all this stuff at either end is just to say that before and after the substring, you're allowed to have whatever you want and as much of it as you want. Okay, that's all we're saying. All right, so let's do a more interesting example. What would be a regular expression that picks out the set of all strings of zeros and ones that have even parity? Who hasn't spoken yet? View. Okay, cool.
So an even number of characters.
Yep.
So
What?
0, 0, or 0, 1, 0, or 1, 1.
Okay, let's start out by looking at that. So 0, 0, or 0, 1, or 1, 0, or 1, 1 star. Okay, so that's certainly a valid regular expression. Now, does it give us all and only the strings of even parity? No. Well, okay, so can anyone give an example of an even parity string that's not caught by this one?
0, 0, 0, 1, 1.
All right. Okay. First of all, okay. I guess that what this is actually giving us, yeah, is the set of all strings of even length, right? This is giving us all the strings of even length, right? So in particular, this could, in the first place, this could give us strings of odd parity, like this one, and there are also strings of even parity that this would not give us, such as 0, 1, 1. Okay, so it's a little bit trickier. Anyone? Yeah.
What if we had 0 star 1?
0 star 1. Wait, 0 star 1, and then, sorry.
0 star 0 star, and then put that in parentheses with the star.
This almost does it. Can anyone see? There's one little tiny issue with this one. Can anyone see the little what? Huh? Yeah. Yeah. This one doesn't catch the string of all zeros. How can we fix that?
Before the parentheses, you just add 0 star.
Yep. There we go. There's our set of all even Hamming weight strings. Okay, and you could have fun writing one for the set of all odd Hamming weight strings. Okay, and there should be some p-set problems about this. Okay, but one thing you notice is okay, we were able to write a regular expression for the set of all even Hamming weight strings. We were also able to write a DFA for that before, right? And in general, the things that we're able to write regular expressions for seem somehow related to the things that we're able to give DFAs for. So we could write regexp for just the set of all the languages that can be specified using a regular expression. And you might wonder about the relationship between this and these guys. Okay, so what you're going to see next week is the amazing fact that actually regular expression equals these two guys. Okay, so it's just another way, as its name might suggest, of picking out the same happy family, the family of regular languages. Okay, and then you'll see a further interesting notion, which is the context-free languages. Okay? Okay.
They're mostly in the art department. I mean, in film. My girlfriend's in film, and that's what she tells me. And she used to be in the art department, but now she's mostly directing and writing. So.
That's funny. I wouldn't be surprised if a lot of videographers just came from like arts departments. Like in
True.
general.
Yeah, it was very artistic. That's what we learned. I tried to get TAs once to do videography, and it's unless you have the aesthetic, it's really tough. Yeah. And practice, of course, helps, but for my dad, he basically jumped into it with almost no experience. He just had the eye. It's impressive. He's hard to replace.
Helps to be excited by the topic too.
That's true, yeah. Care about the lecturer.
It's generally true in all of life. Yeah.
Yeah.
But that's another thing.
All right, we can go in.
And you have good food.
Oh, I have... I wanted to tell the videographer something. I have a surprise for today's lecture, which are some temporary tattoos. So just putting that out there, at some point you might want to zoom in, one of you, or something. Something funny. Doesn't have to be super zoomed. It should be pretty visible. That's the intent.
Which arm is it on? The right?
Both arms. I'll do one and then the other.
All right, so you have to do it because my camera doesn't zoom in close enough to do that. I would say
I mean, you don't have to get super close. But